First, I'd like to introduce the METEOR project, which enabled the creation of this video. METEOR stands for Modelling Exposure Through Earth Observation Routines and was funded by the UK Space Agency through their International Partnership Programme as part of the Global Challenges Research Fund. The METEOR project aims to develop innovative application of Earth observation technologies to improve understanding of exposure. Natural hazards have had escalating impacts, which are contributed to by an increasing exposure of population and assets. However, a major challenge when making disaster risk management decisions can be a poor understanding of the distribution and character of exposure. Robust quantitative methods are required to justify these decisions, and in this project, we are looking at the use of Earth observation technologies within that context. Within the METEOR project, there is also the aim to share knowledge. This video is produced as a part of a series of educational videos to enable the use of METEOR products and data.
All right, I'm Charles Hike, Executive Vice President at ImageCat, and I'm going to be introducing the topic of building exposure, talking about it in general in the context of loss estimation and CAT modeling, and also focusing on the work that was done as a part of Project Meteor. So the purpose here, this section will introduce key concepts to a general audience, such as data resolution, difference between aggregated and building specific data, and what is key for assessing vulnerability. So that's the purpose of this section. Major takeaways. At the end of the presentation, you'll hopefully have a solid grasp of what exposure data is and how it is used in loss estimation process. Basic process of developing exposure data, the value of Earth observation data in the context of building exposure data, and how to check your exposure data and ensure that it's fit for purpose. All right, so drilling down into each of those, what is exposure data and how is it used in the loss estimation process? I'll be covering what is exposure data, levels of exposure data. That's something that we've come up with on the Meteor project. I'll be discussing those in detail. An introduction to the idea of spatial resolution, building vulnerability attributes, talking about replacement costs, vintage, as well as talking about some challenges and expectations people often have when of building exposure data, what you can reasonably expect from building exposure data. So what is building exposure data? Often when we talk about building exposure data, we go in and start to talk to people about risk projects. Right off the bat, they think of this type of data, which is, I think, a virtual 3D representation of buildings in a very urbanized setting. This is not what we're talking about. This is not the type of building exposure that we're talking about. That type of building exposure data is used for rendering, could be used for planning purposes. But essentially what the focus here is to capturing what buildings look like. And although it does have some sort of aerial representation, it doesn't have sort of the type of square footage, replacement cost, structure type information that we would use for estimation. So instead, we're talking about really the art of distributing inventories of people into estimates of buildings throughout a given area. It's a process that's very specific to loss estimation itself. Answers the question, given a number of people, how many households are there going to be? How much dwelling area is associated with those households? And then given that, what is the replacement cost? Structure type that can be used to assess damage from multiple hazards, and then how does this change throughout a given area that you're looking at. So this is the type of information that we're talking about. This is a representation from come out of the Meteor project hosted by Jim of what that looks like for the LDCs in Africa. I guess it's all in Africa here in this presentation. So what this is a gridded representation. For each of these grids, you have an estimate that you can click on and reveal the replacement cost in thousands of dollars in this case, mapped throughout the area, and for each of these cells, how that replacement cost is distributed in terms of these codes. These codes here map directly to a vulnerability assignment that you can cross-reference with, say, ground motion or depth of flooding to get an estimate of damage. In this case, these are specific for earthquake. And that's really what we're talking about when we're talking about building exposure data in this context. It is different than an inventory. An inventory of buildings might be if you have thousands of buildings in your town that are a particularly vulnerable area, and you want to get details of each of those buildings for the purpose of looking at mitigation options or retrofitting or what have you. You could say that that's a building exposure at the end of the day. That would be part of what we would call a level 5 building exposure, but it's really different, tends to be different purposes. That would be for sort of a portfolio analysis or municipal management purposes. What we're talking about in terms of building exposure is typically an inference process over a wider area. So when people talk about building exposure, they're generally not talking about a building inventory, although they could be interchangeable in that sense. But a building exposure database that we're talking about is definitely not a building inventory, although the other way around might work, arguably. And here's another example for Haiti. You can see in this case, the scale is such that you can see the individual grids, and you can see that it's largely an estimation process. This is a global product that we've estimated here, so this will be referred to as a level 1 product. And you can see in certain areas in the right by the bay there, I'm sorry, by the internal lake, there are areas where you can see that there's building stock that weren't able to be captured by the process. So there is error involved in the process. It is an intelligent smearing, if you will, and it's important to understand how that's done, where that comes from, in order to use the data appropriately, which will be some items that we'll touch on later in the presentation. And here's another example for Tanzania. It just has the raw count of the buildings throughout the area, and you can see the urban areas such as Dar es Salaam might be quite intense in terms of the number of buildings, and then it's distributed all throughout the country, throughout the various rural areas. And in this case, in both cases actually, it's a 15 arc second, which equates approximately to 500 meters, depending where you are in the world. So there's different ways of putting together, many different ways of putting together building exposure data. And at the end of the day, you receive this building exposure data, and in many cases, you're not quite sure what you have, or how it was developed, or what the process was, or what how dependable it is. And people try to use that, have to use that to make decisions, often without understanding the limitations of the data. So as part of the Meteor project, one of the things that we tried to do and tried to reinforce is appropriate use and understanding the scale of the data. So we came up with the idea of scales and levels depending on borrowing a lot from the GEM levels that were already in place, but also the literature and so forth, so that there would be a way to refer to the actual taxonomy, to refer to the process that was used to put together the data in a way that you could communicate to others what has happened. So We came up with 5 different levels, and here they are represented for Los Angeles County, which was used to represent uncertainty in the project as well. This is why it's in Los Angeles. But here we have 5 levels of data represented that we collected for Los Angeles. So the first level would be global scale data. So that's data that would be collected using global data sets and make assumptions from there. Level 2 is where you collect national data and use that to put together an exposure database. Level 3 is where you augment that with local information. Level 4 is aggregated up from building specific data, and level 5 is essentially building specific data. So if you look at each of these, you can see that there's quite a bit of difference in terms of the spatial representation of, in this case, the value of buildings. As you go into level 3, 4, 5, you can see what's actually the Wilshire corridor coming up from the coast there. This line of purple gets sort of more distinct, more or less distinct, depending on which data source is used. And it becomes crisper, almost like something is brought into focus. And that is because of the scale that's of the data that's used. So as you get to level 5, you can really start to see the changes in density throughout the suburban areas of Los Angeles, whereas that is much less clear in types 1 and 2. So, likewise, you can see between 2 and 3, there's quite a bit of difference in terms of how that weighting and value is represented as you move out from the center of the city. So we'll talk about these levels in a little bit more detail as I go along here. But an important thing to remember is even though you've got a representation that goes from quite arguably quite crude at the global level to building specific data, you don't necessarily get a better understanding of what risk is. Resolution of data is not accuracy of data. And we did some interesting experiments with the data sets that are represented here. And what we found is just that, which is an important lesson, I think, for the community to come out of the project. All right, now I'm going to go through those levels in a little bit more detail so that you've got an understanding of what they are. And so we talk about level 1, level 3, level 5 data. You'll have an understanding of what that means. Level 1 data set, as I said, is global data. It's typically global, but it can be continental or regional. It's data that was not collected at the country-specific level, but essentially it tends to be an aggregate of aggregates. It can be based on global population data sets with some assumptions, with just a few things that are tweaked from for a specific area. But the purpose is essentially to do a level 1 to get something that can be used very crudely to assess risk and figure out where you might want to take a closer look. Level 2 is country-specific exposure data. A good example here is displayed on the right. That's actually the HAZUS data, the HAZUS US data base behind the FEMA product. It's when you've collected all of the data, the best data that's available at each point in the exposure development process at the country level, and bake that into the best level 2 exposure database that you can. So typically, if there's any regional adjustments in things such as household size, number of people per household, and so forth, that will either come from the census or based on just a real limited change that an expert might make. So obviously, if you release level 2 and say a specific municipality is trying to make decisions, it might not be the losses that you get and the results that you get from a level 2 analysis may or may not be appropriate. Typically with these national packages, They might be run at the state level or run to come up with national reports. But if a local entity wants to use it to come up with their own hazard mitigation plan or what have you, they would take that and have experts augment that data to come up with a level 3, 4, or 5 data. We'll discuss that as we move along here. There are key pieces of information that have to be brought in to make this exposure database that are done at the national level that are worth noting. Structural type distributions are typically quite crude on national level with minimal local adjustments. A number of people per household. That's a key statistic, and coming up, as we'll talk about throughout the results here, number of people per household is key in getting to an estimate of actual square footage distribution of buildings, as well as the replacement cost. The number of people per household in a level 2 would hopefully come from census data, and if not, the assumptions that are made at the nationwide level can really cause a lot of error. Again, also household size, that's a tougher one, not typically inventoried by census, but where it is, countries where it is, that can be used and makes the data quite a bit more accurate. But if not, if you say the average house is 1,500 square feet or whatever, that will cause error as you move geographically out through different climate regions and economic conditions and so forth, where that assumption may or may not hold. And then finally, the building replacement cost per square meter is also a key determinant of the final results, which when you have that estimate at the country level, that's be problematic and cause error. Now, level 3 is when you basically have that same type of national data that you use as a base, but you've gone in and made significant changes based on looking at those key variables and looking at how they might vary throughout a specific region. So here's an example. I believe this is for Addis Ababa in Ethiopia, where you take a closer look at things like construction patterns, how that might vary throughout a given country, what the difference in fragility would be in a given state that might have done quite a bit of work to look at things like hazard mitigation and so forth. Identifying major urban areas and enhancing building counts, structural mapping schemes in those areas, particularly in high hazard areas and so forth. So it's essentially taking those key variables that I was talking about above, the vulnerability assumptions, people per household, and the replacement costs come to mind, and trying to figure out how those can be fine-tuned, modified on a state-by-state level or areas that, or at least by region, to come up with results that are more accurate. That can be as simple as integrating more census data, or sometimes it's more difficult where you have to really drill down and have structural engineers look at areas, or get cost reports that give you a better handle on what's going on throughout a country. Now, level 4, now we sort of change paradigms. Level 1, 2, and 3 started from GIS data aggregate that has already essentially been aggregated by information that was collected locally, largely through census data, and figured out a way to essentially distribute that to a gridded or more localized area. With a level 4 analysis, you're starting with building specific data and aggregating that up to make a decision. So that tends to be, not always, but tends to be a more regional analysis. It might be a county, as we did for Los Angeles there, or it might be a tiny area of county, or you might have significant with EO data and building extraction. You might have data for all of California, for example. And you'd be able to aggregate that up with some of the Microsoft building footprint data or OSM data. That becomes more reasonable to do if there's a complete survey of an area, but you have to be very careful. Now, why would you, if you have building specific data, why would you create this aggregated and not just look at the building level data? There's a lot of reasons. Typically, if you do have building specific data, it's not going to have a lot of the information that you need to perform a risk assessment. It's not going to have detailed structural information. It's not going to have, might not have information on the number of stories, for example, or it might have replacement costs that are collected for a different purpose. So by aggregating that data up from the detailed level to an aggregated level, you're able to make, to overlay, if you will, assumptions about modifiers or the distribution of attributes that aren't collected at the building specific level that you can then use for a loss estimation project. So say, for example, if you have OSM data that's complete for a given region, say this region, which is Dar es Salaam, you could use that building footprint data to come up with an estimate of the number of buildings and the square footage. But the OSM data might not have complete information about the number of stories. Likely it won't. And it might not have any information on the vulnerability. So you would take that OSM data, aggregate it to that gridded level, and then on top of that, perhaps come up with a structural distribution of the vulnerability attributes that are available on a gridded basis or on a neighborhood basis, and then apply to those grid cells. Likewise, if you don't have a number of stories, you might divide the city into different classifications and then come up with a distribution that you are then able to apply for those grid cells, which would provide a multiplier to extrapolate the total square footage of buildings from the the square footage of the building footprint. So the level 4 builds on building specific data. Arguably, you would think it would be more accurate than a level 3 data because it does have that distribution of buildings. It does build from that distribution of buildings on a site-specific level. But it still, depending on the data that you're starting with, it is not necessarily more accurate, which is something we need to keep in mind. Level 5, site-specific data. This is when all the data is provided at a site level. So this arguably is a building inventory, although it's not necessarily a building inventory for a risk assessment project. So for example, if you do have, again, going back to the OSM example for Dar es Salaam, if you do decide, if you're looking at flooding results, for example, and you really want to get that site-specific answer in terms of where things are spatially, you don't want to aggregate up to a larger level because you're worried about the way that would intersect with the flood inundation polygons, for example. So you decide to use that site level. What you can do is take those attributes that you would have at the gridded level and sort of push those down to the site-specific data level using a randomized process. And if you understand that that's what you've done and the limitations in that can be very powerful for looking at very localized hazards, such as landslides and flooding. The risk there, however, is if that data set is used by somebody else, then they might bring up a building, and without knowing that you've randomly assigned building heights, or without bothering to read the metadata, they might say, oh, this is a 1-story, not a 5-story building, and that has a reputation hit, or they've decided to plug that into their tax assessor data because they got, I mean, all sorts of things can happen when the data leaves the office, right? So there's a risk there in that the data could be misinterpreted and misused later down the line. But a level 5 data can be something where the data has a much tighter relationship between the attributes and the level of analysis that the loss estimation analysis, where you're able to use that data without too much of augmentation, or maybe you just have an uplift factor. For example, if you have a valuation used for tax assessment purposes and it's a few years old, and you want to adjust for inflation, for example, you can do that uplift without too much risk. So each of these levels are really meant to communicate sort of the resolution and the methods of coming up with a building exposure database to communicate, but it doesn't cover those details. Those details still have to be documented and communicated to the end users in a way that they can consider it. In terms of both understanding the risk analysis that's done specifically with the data and what the appropriate uses are for the data sets if they're trying to repurpose it for other projects. But it does not communicate the accuracy. We're going to get into that a little bit more later. You can have a level 5 data set that is less accurate than a level 1 data set for a specific purpose. So I'll be talking a little bit more about that later. All right, so we've already talked quite a bit about sort of the inherent resolution here about data without talking about what spatial resolution is. So make sure that you have a concept of that. Spatial resolution is it's the unit at which the data is posted. So in this case, on the left here, we have this is Los Angeles City, and these are, I believe, census tracts. And the spatial resolution of that data is the census tract level, you would say. It's not an even unit geographically speaking, because some of these are quite tiny in areas that are dense, have dense population, and then some of them are quite large. In this case, these are in mountainous regions. So it's not even geographically, but the spatial resolution, we would say, of this data is at the tract level. You could have, and this is all for the city of Los Angeles. If all of that data was 1 point at the city, you would say that that resolution was at the city level. You can have the county level, the state level, and what have you. So you can have units that are associated essentially with administrative districts, typically. Although you can even have uneven polygons that are not associated with administrative districts. But that spatial resolution goes down to a unit of polygon that's typically named. And the way that you typically see it would be a census tract level, city level, county level, or state level. But there are different levels of aggregation. But it's important to remember that sort of an uneven vector level of resolution that is typically associated with GIS data sets. And the one in the middle here is a gridded data set. In this case, this is not exposure data. This is hazard data that's posted on an even grid. And I can't remember what the resolution of this grid is. This is from the Northridge earthquake. In this case, there's contours around these. This is the PGA. There's contours around those grids, so you can see the difference between the contours and the grids. And that resolution would be expressed as the actual dimensions of that grid itself. Typically, they're either in a latitude-longitude unit, in which case it's going to be uneven in terms of what you've got vertically and horizontally, so it's not a square on the earth, and you can see that here. These grids are oblong, rectangles actually, instead of squares. or you might have a 100 meter, 500 meter grid, and so on. So typically what we would have is a expressed in units of arc seconds, 15 arc seconds, 30 arc seconds, and so on, which correlate roughly with a kilometer and a 500 meter grid cell, depending on where you are in the Earth. But it's a gridded data set. And of course, how accurate that is really depends on the process that needs to be understood. So you can have a 15 arc second database that's based on a global product, or you can have a 15 arc second database that's based on aggregating up from OSM data that you had for a specific project. Very, very different in terms of the resolution, the accuracy of the number of buildings at that specific location. So it's very important to understand the difference between spatial resolution and the accuracy. And you can post data at pretty much any resolution that you want. That's not going to make it more accurate. And to the right here, we just have an illustration of if you've got administrative data and gridded data, and you try to cross-reference those two, you'll have a disconnect between, well, not a disconnect, you'll have assumptions that have to be made where some grids have, some administrative units have many grids within them, and some grids have many administrative districts within them, in this case, census tracts within them. Just because, again, because you've posted results at a very fine level, in this case, the census tract level, doesn't mean that the data behind that has meaningful variation of observations throughout that level. So in this case, this results were generated using this very gridded product. So in areas with very small census tracts, that variation that you see in terms of the results are only because of variations in the exposure, not because of variations in the hazard. Whereas these larger polygons add many different observations of the hazard that went into it. So, I mean, you have to be very careful to understand where the data came from and not take it at face value in terms of the spatial resolution, in terms of the accuracy. All right, next, discussing building vulnerability attributes. I'm not going to go into too much detail here because the attributes of buildings that are required for loss estimation vary greatly by hazard and by vulnerability functions that are used in a given risk assessment product. But essentially, first we want to sort of introduce the idea of what they are. So if you look here in terms of the upper right, here we have, looks like 6 damage functions related with flooding. And what this is here, if you look on the axis, this is the water depth estimated in meters. And this is the percent of damage that you would expect, the damage factor, which can easily be translated into a percent that you would expect given that depth of flooding. So what it says here is if you look at the level 1, there's about 90% damage is expected if there's 1 meter of water, whereas this one on the bottom in purple, you'd only expect about 30%. Now, I don't know what types of buildings they are, but just without knowing anything, I know that the building materials associated with one are much less resilient to flooding than they are at level 4. So level 4 might be a brick building or a steel building, whereas a level 1 might be an informal building. You'd have a very different damage factor if you were looking at, for those same types of buildings, if you were looking at earthquake, for example. So if you've got a brick building, might be much more hazardous than a wood frame building, for example, which would be more damaged in a flooding event. So for each type of these hazards, you have many different attributes that can go into the vulnerability that have to be represented or that can be represented. So right off the bat, number of stories is very important, both to look at the exposure that's on the bottom floor to floods, or the spectra that it's most vulnerable to for earthquakes. First floor elevation is something that we often look at in terms of flooding, because that tells you where the water is going to start to get into the first floor where it can cause damage. The structural materials that it's been made of, whether it's informal materials, indigenous materials, wood, light wood, brick, what have you. Lateral force resisting system. This is much more complicated in terms of earthquakes, looking at what the structure of the building is made of and how that responds to shaking. Whether that there's been retrofits is something that's quite key in some risk projects. Nail density, that's one that's almost that's quite important for looking at roofs for hurricanes, for example. The more dense the nails are, the less likely those shingles are to fall off, and the exterior of the building compromised so that the wind can go in, and then that starts to do quite a bit of damage. So that one factor can have that's very specific, that it's very difficult to inventory. Can make a big difference. And even the distance between buildings is an example. So I've taken just these sort of overview of the types of things that we look at, what you're going to look at for a specific exposure development product is going to depend on the hazard that's relevant to that area of the world and what your purposes are. So the reason I've chosen some things like nail density, retrofits that you can't see, is to make the point that a lot of these things are going to have to be inferred, and they might be inferred from things like when structures were built or when that neighborhood was built out, which are either assumptions that you can make from satellite data or you can make based on detailed tax assessors data. So or you can have people go out and inventory structures and try to make an assumption from there. So there's a lot of different things that you can do. We'll be talking about some of them in a little bit more in detail later when we talk about putting the databases together. And Vitor in his presentations will be talking about vulnerability as a concept in quite a bit more detail as well. Now moving on to replacement costs. The first question that you have often with replacement costs is what is it? A replacement cost typically is referred to as the price it costs to rebuild a structure. And as you can see, the damage functions are often applied directly to that number to have that damage factor to get that 85%. That 85% gets multiplied by the replacement cost to yield what the damage is. But there's a lot of debate as to whether that replacement cost value actually includes the cost of demolition, whether it includes architectural costs, whether it includes a depreciated value in terms of what a building is worth now that it's, say, 100 years old, rather than if it's a structure that was built just this year. And there's no easy answer for this. The damage functions don't typically take that into account. So what we tend to say is be very clear in terms of what the number that you're using represents to you for that specific project, and document that so that others will know when they use it for a project. And that's really the most important thing to say. I mean, the damage functions are not refined enough to, and the results that come out of these loss estimates are not really refined enough to have a different curve for architectural costs, for example, or demolition. But if what we assume is if there's 85% cost in there, damage in there, for example, which is less than 100%, that the other costs that you're going to have that are going to go in are going to scale proportionally. So we just put in one replacement cost. We don't have different damage curves, but it's clear that you need to be very specific about what you're putting in there, so that others know. You're looking at typical replacement costs. So what does it cost to build a wood frame structure, for example? You're not looking at exceptional. You're not trying to capture the range of buildings. It's it's really what the typical costs are for that type of structure. At the resolution, if you have information on how that varies by census tract, by all means use it. But you're not typically looking at building specific values and trying to look at architecturally tricky buildings and so forth. Tricky to develop. It can be very, very tricky to develop, and it's not always meaningful. So here in this lower right-hand side, I've got a picture of this hut. I just love this picture of this hut. It's amazing to think how that was put together. It's just ingenious, but the replacement cost by some metrics would be zero, right? And that would be zero because whoever built the hut probably wasn't paid. It was probably their own home, and the materials that they used to build it out of, they've probably collected themselves. So there's been no exchange of money for labor, or they're say for argument's sake, and there has been no purchasing the data from a source that can be monetized. However, obviously, there's a lot of work there, and the disruption of that, the damage of that from a flood, for example, needs to be accounted for. So it can be very tricky in terms of trying to evaluate non-traditional structures in terms of money. And as long as you've understood that that's what you've done, and if you can communicate that, that's all right. But it's important to make bare your assumptions. You can correlate with income. This is something that is, I think, really important to understand. People generally build the best home that they can. If they've got more money, there's more expense that's involved there. So there's a human factor that also needs to be captured when you run these loss estimates in terms of population exposed. But having that replacement cost vary by economic activity can be really refine your results. In terms of sources, there can be all sorts of sources, but you have to be careful in how you apply them, of course. Here's three types of ways to come up with replacement costs that we use in various circumstances. One would be the one in the middle here for Senegal, would be resettlement action plans. In this case, they were developing, well, let's see, I guess it's not in English. They were developing a dam or building a highway or doing something. And where they had to purchase buildings to get them out of the way, and they've negotiated a fair price with the locals there, or what they decided was a fair price for this project, and in doing so, provided a valuation per structure that we can use to come up with a square footage value if there's enough detail in that report. We find those very powerful. Other sources, this JRC report here, that has global depth damage functions, also has valuation of structures based on GDP. Quite a clever method here that we've used in various circumstances. And then just looking at one of the regular pricing surveys by, generally speaking, would apply towards only the most robust construction. Okay, vintage. Vintage is can be very, very important. Here we have a PopGrid viewer that looks at different population data sets that are available globally. And in this case, they're providing the vintage of a single data set, GPW, Global Population of the World, version 4.11. And it's telling you how old the data sets are. And these red ones are 2001 to 2005. The yellow ones are 2006 to 2010. And the blue ones are the only ones that are since 2010. In this case, they only go up to 2015. So in all those circumstances, those data sets are going to be old. Those population data sets are going to be old. And if you're basing subsequent um, uh, extrapolation of the number of buildings, the square footage of buildings, and replacement cost on those old populations, you're going to introduce error in terms of where construction has been, where there's been development within a country. You might not, some cities might be less represented than others. And as a whole, you're going to be off. So if there's a 10% growth in a given country since 2006, for example, you're not going to be able to capture that. It may not be a big deal if you're looking at countries where there hasn't been a significant amount of development. But generally, if you're trying to use the numbers that come out of here at face value, you want to at least sort of scale based on estimated population statistics, which can be obtained from groups like the UN, or you can even find things on Wikipedia. But vintage is a key determinant that people don't often consider. So challenges. You've had a whirlwind tour of what exposure data is and what some of the components are. I've introduced some of the challenges along the way, but these are things that you need to think about when you're putting together exposure data, or that you need to consider that others might have done. First is data availability. When you're trying to get these data sets, it's sometimes very hard to put your hands on them, and if you even find them, it's you might not get permission to use them for a given purpose, or there might be a charge that actually makes things prohibitively expensive in some cases. So those can be challenges. Processing challenges, obviously, taking all these various pieces and putting them together with GIS and remote sensing software into a product can be a challenge. It takes a lot of different skill sets. You need to have a lot of GIS work, but you also have to have structural engineers involved as well to help make the decisions in terms of vulnerability. So that's a skill set that not a lot of folks have. That can present quite a bit of challenge. Bias. When you're putting together these data sets from multiple sources, there's likely to be bias in those data sets. As I mentioned, the population, just even that if the vintage is old, that's going to be bias away from areas where there's been more growth. But bias in terms of census, sometimes census isn't as thorough in some areas as others, and all sorts of bias. One thing I think I've mentioned, aggregating up OSM data, which can be very powerful, but also introduces bias because you've then sort of looked at only the areas where there's been OSM projects or people have decided to contribute to OSM, which again, might be towards areas where there's universities, for example, and perhaps less in rural areas, just depending on the country. Human error. A lot of steps to put all these pieces together, and it's very easy to make mistakes. That's why it's very important to look at what you've done and make sure that it makes sense, even if you think you've done every single step independently right. When you look at the final product, you might find things that stick out, and having folks that were not involved in the development process take a look so that they can see as well. Data gaps. No matter what you're doing, there's going to be something that's not available. That's something that you don't know, where there's going to have to be some sort of inference. And you're going to have to guess. You're going to end up getting the right people that are appropriate to make that guess. is ideal, but sometimes those people aren't available and or not answering your emails, and you have to make that guess yourself. So that might be something like the height distribution of buildings in a certain area, or it might be something like the number of nails in roofs and how that varies by year built, for example. There's a lot of assumptions that need to be made, and this is why documentation of the process is so important. One that I face quite a bit is misperception of the data. You know, it's very easy to look at those grids and see the count of buildings in a GIS map and say, oh, well, look at that. That looks great. It seems to vary where the population with the population, and it must be perfect. But not understanding the assumptions that have gone into it, and what the data gaps were, what the limitations are, is a challenge, and one that we've tried to address here by first introducing the levels, but also really focusing on the documentation and the metadata that's provided along with exposure products. So having people take a look at that is a good chance to dispel some of those misperceptions. Accuracy. It's a tricky thing to characterize, and the validation is a tricky thing to characterize because you have so many pieces and so many data gaps that are part of the process. For example, it's hard to say, well, the results are accurate to within 50%, unless you have some completely independent way of getting that and checking that at a building level. And with the losses, you know, if you're talking about how accurate are the losses, the losses that will result and the risk that results from using one of these exposure databases when cross-referenced with a hazard data and vulnerability where there's quite a bit of uncertainty on those components as well, becomes extremely difficult to characterize indeed. So that has to be considered when using the data. It's really something where you have to sort of understand the process rather than can be given something plus or minus 50%, for example. And that leads right into the next challenge, is false precision, and that is taking those results that have essentially been extrapolated at a local level and using that, for example, to make a decision as to where to fit a specific building, rather than a community or type of building, for example. You want to definitely, when making site-specific decisions, take into account what you can see with your very own eyes to augment the results from a loss estimation product. Explaining the data with clarity. So I've hit on a lot of different topics, even in this just beginning introductory section that illustrates some of the complexity here. It's important to be able to describe what you've done with some clarity. We'll talk about a little bit more about that in our metadata section. Inappropriate legacies. I've referred to this a few times in this presentation. This would be if you've collected data for one purpose and it's reused for another purpose. And this can be, it was reused in 10 years and it's no longer suitable for a given community. Or it can be the planning department got a hold of it and is using it to decide how many people to send out to do surveys, for example. It's really the repurposing of it that you're worried about. And some other challenges: turnover. A lot of times people who've put together these data sets and put a lot of effort into coming up with these exposure data sets over a few years go on and get other jobs. If you've the national level, if there's turnover in terms of exposure development projects, the legacy of being able to understand how that has happened and to be able to do it again can often be quite a challenge. And this last one is sort of a nice problem to have, is advancing technologies. There's a lot of changes in uh, artificial intelligence, UAVs, additional sensors coming up. SAR is now a lot more prevalent. Being able to understand how to use those sources to intelligently augment the development process, exposure development process is a challenge, but it's a nice challenge. So AI, for example, a lot of folks are running analysis on street view data and being able to do things like infer the number of stories, or whether you've got soft stories, or whether you've got a residential or commercial district, how to use that data that's site specific, along with other data sets to develop data regionally, for example, is a challenge. UAV comes up with some amazing representations of buildings. How to use that to augment building inventories or building exposure is a challenge. And this gets right into the expectations. Cannot typically expect an accurate number of buildings at the cell level. The count is approximate. Now, if you've aggregated up that with a level 4 data set, that might be an exact number. But typically, that's not something that you can expect will be there. You can expect more accuracy than the original base data sets, right? You're not going to have a census that was taken 20 years ago. Try to do your best to come up with a building exposure database and do a better job than the original census data. Even if you've scaled it, it's just not going to be able to have capture that distribution. Cannot always expect to capture small unmapped rural areas, even with remote sensing data. This is a continuing challenge. And if you've got a project where that is important, for example, you're looking at landslides, then you're going to have to really do some focused reconnaissance or some manual work there. Challenges in remote sensing data sets will impact the results. There's some areas that are almost always under the clouds. Very, very difficult to see. And if the clouds aren't there, guess what? There can be tree canopies over structures at all points in time, and you won't be able to see those from a remote sensing project process. Lighting, the night light data, VIIRS data is really great for being able to capture rural areas in a lot of cases, but some areas do not have any lighting at night, and that can be detected from space. So that makes it even more of a challenge. Also, when you've got situations where buildings are hard to distinguish from vegetative material, for example, if you think of the hut, very difficult to distinguish that from a bale of hay, for example. It's just the building materials is what, and the difference between man-made building materials and natural materials is really what allows us to detect that. Some areas that becomes very hard if you don't have that's kind of stark roofing material. It allows you to detect these things. And again, I've made this point a couple times, cannot repurpose the data for civic purposes, such as address-specific information for tax purposes. This comes up quite a bit. I'm going to put on the right sustainable development goals, end poverty, sustainable cities and communities, climate action. All this SDGs and the Sendai framework, answering these questions at the national level, where you have to make tough decisions in terms of how to put forth these numbers at the national level. That's really the type of thing that these building exposure databases can help with. All right, now I'll be talking about the basic process of developing exposure data. Developing exposure data